Today we're going to be looking at something called slope, or rate of change. This is a really important concept for the grade 9 course, and in fact the next few days are going to be looking at this idea. Today we're going to be looking at it in how it relates to tables. Tomorrow, or next lesson anyway, we're going to be looking at how it relates to graphs, and we're also going to be looking at a formula for coming up with this. So after we have this, then we're going to use it and we're going to carry on. We're going to make up equations of relations. Remember, we introduced what a relation was recently. And so we're going to be working with relations for a long time. And slope is a really big part of it, or rate of change is a really big part of it. All right, so just trying to set the stage for us. So the first thing that we need to know is that rate of change, slope, basically we're referring to the same thing. So you can see both those words are in bold. I've just highlighted both of them in the lesson. So I'm going to use these two terms interchangeably. But rate of change is defined as change in one variable relative to the change in another. Remember, when we're talking about relations, then there's always two variables, right? Often we use x and y, but it could be other things. If you think about the example I did a couple lessons ago about window washing, I think the two variables I used was w, and c. W for number of windows, c for cost. So how does one of the variables change in relation to the other one? And that's rate of change. You know, it can change faster or it could change not as fast. In particular, in the window washing example, if Blake was to charge more per window he washed, then that would have a greater rate of change. In other words, the cost would go up faster than if he charged less per window he washed. All right? So that's what rate of change is. When we talk about slope, usually what we're talking about in particular is the graph, because if you see a graph of a relationship, then the rate of change is going to look, the line will look either more steep or less steep. And so then that's a visual of how rate of change works. And if you actually look at it, think of a rooftop. When you're looking at a roof or a ski slope, when we talk about the slope, we're talking about how steep it is, right? We can have a really steep roof. We can have a really steep ski slope on a mountain. And the steeper it is, the greater the rate of change as far as how things are going up or down. And so again, graphically, that just means the exact same thing, except in particular as a graph. So just to give a little visual of that. Nope, not there. Let's try again. There we go. So here's a graph. And remember, another example that I've used a couple days ago was distance versus time, right? So imagine you're on a car trip and we said that T stood for time. That was how long we'd been driving, and D was the distance we went. And so remember T, well, one of them has to be the independent variable, the other one is dependent upon it. So in this case, time is independent. We choose, I can choose, well, how far have I gone in, 1 hour or 2 hours or 3 hours and so on. So that always goes on the horizontal axis. The distance just comes as a relation in relation to that. So maybe I've gone 100 kilometers in 1 hour, and maybe I've gone 200 kilometers in 2 hours, and so on. Right? And so if I do this graph up, and then I connect the dots, I'm sort of doing it backwards here, but if I was to do that kind of thing, then I would get this straight line. And if you look at this graph, it's got a certain steepness to it, right? So that's the slope. That's the rate of change. Think about this person would be going 100 kilometers per hour, the way I've got it set up here. But imagine they were driving faster. Maybe they were speeding and going 150 kilometers per hour. what would happen if I was going 150 kilometers per hour would be after 1 hour, I'd have gone 150 kilometers. After 2 hours, I'd have gone 300 kilometers, represented like that. And if I was, I'd still start at 0, 0. And if I was to connect these, look at that red line there. Now we've got a steeper slope, a greater rate of change. So if I drive slower, maybe I'm only driving 50 kilometers per hour, well, then that could be represented. I won't bother doing points, but maybe 50 kilometers an hour would look something like this one, right? And again, you can see where the term slope comes from. The red line is the steepest slope. The blue line's the middle one. The purple line's the least steep slope. But that's also the rate of change, how far someone's going compared to how long they've been driving. So this idea of rate of change doesn't just apply to distance and time. It can apply to all kinds of different things. And so that's what we're going to be working with for the next little while. And we're not going to be really working with graphs today. I just use that for an example. Today we're going to be really talking about how we can recognize rate of change using tables. All right. So given a table of values, we calculate the rate of change using this formula. So ROC is just short form for rate of change. And that says triangle y over triangle x. That triangle, we actually we call that delta. So delta means change in. Okay. So delta triangle means delta, and that means the change. Okay, so delta y means change in y. Delta x means change in x. So rate of change can be defined as the change in y divided by the change in x. And change in y is just the first differences. So if you think back to what we learned last lesson, I believe it was, first differences was actually just the changes in y. We saw that was when we were talking about linear versus nonlinear, but if we're focusing on linear right now, remember first differences were all constant, and so first differences were just the change in y, and delta x is just what the x's are going up by. So that would be our formula that we're going to come back to, all right, for rate of change. So again, this is an important formula. Keep this in mind. Maybe I should put a little box around it just to highlight it a bit. Okay. Can you think of examples in everyday life that have a rate of change? Well, there's all kinds of things actually in everyday life. Some examples that spring to my mind might be stock market over time. Stock prices go up and down over time. Height versus distance. Think about if you are skiing or snowboarding. So if I think about height as being up and down, say I'm standing at the top of a mountain and then I start to ski down it, well, obviously my height is changing as I go down the mountain, but my horizontal side-to-side distance is changing as well. So that would be another example of a rate of change. The steeper the slope, then the faster the height would be changing compared to the vertical distance. Or height versus time. Imagine I've thrown a ball up in the air or something like that, or kicked a football. The height of that ball is changing as time goes on. Now, not all of these are linear. They're not all going to be constant rates of change, but they all have a rate of change associated with them. And there's all kinds of other things that we can, basically anything that has a relationship between it, if we can make up a relationship, then it's going to have a rate of change. All right, so let's look at a couple of examples how we're going to do this. So the first one, determine the rate of change for the relation shown. Be sure to include units when appropriate. So remember, relations can be shown as tables, they can be shown as graphs, they can be shown as equations. So here's a table that shows a relation, and so the x's go 0, 1, 2, 3, 4. That would be our, if we see what they're going up by, the x's are going up by 1. From 0 to 1 it's up by 1. From 1 to 2 it's up by 1. Each one of these is going up by 1. That's our delta x. That's our change in x. And then if we look at the y's, then we're going from 3 to 8. So we're going up by 5. And then from 8 to 13, we're going up by 5 again. And 13 to 18, up by 5, and so on. That's called, remember, first differences. But that's also delta y, change in y. But we have a name for it, first differences. Okay. Determine the rate of change. Okay, well, the rate of change, I'll do it down here. ROC, rate of change, equals delta y divided by delta x, or change in y divided by change in x. So the y's are going up by 5 each time. The x's are going up by 1. So the rate of change is 5. So that gives us an idea of how fast one relation, the y's, are changing in relation to the x's. If I graph this, then I have the ordered pairs. I have the ordered pair 0, 3, 1, 8, 2, 13, 3, 18, and 4, 23. Connect those dots. What you notice is a couple things, hopefully. One, you should notice that this is a linear relation. It's a straight line, in other words. You might also notice that the steepness of 5, if I go from over by 1 and up by whatever, going from one point to the next, let's say I just randomly start at this point here and then go up, what you'll notice is it goes over by 1 and up by 5. So there's my rate of change. So again, it gives me an idea of the steepness. So ROC shows the slope or steepness. All right, let's determine the rate of change in the next example. So here, we're going from, here's my delta x, let's call it that. So going from 9 to 3. So it's going down, first of all, from 9 to 3. So we need to indicate that with a negative sign. That's important. And it's going down by 6. So it's negative 6. Going from 3 to negative 3, picture a number line. So if we count down from 3 to negative 3, we're going down by 6 again. 3 down to 0 goes down by 3, and then from 0 down to negative 3 goes another 3. So we've gone down by 6. And then again, picture the number line going from negative 3 to negative 9, where we're going down by 6 again. So that's my delta x. My delta y, or my first differences, I'll refer to them as first differences because that's just a term that we use a lot. Going from 2 to negative 2, again, it's going downward, but this time it's going down by 4. And from negative 2 to negative 6, it's going downward by 4, and then down by 4 again. So it's constant. The rate of change is going to equal delta y. I'll put the delta y in here just to remind you, but delta y over delta x, which equals negative 4 divided by -6. We know that two negatives simplify to give a positive, so those two negatives basically cancel each other out, so that's the same as 4/6. That can be reduced to 2/3 because we always reduce our fractions. So our rate of change can be given as 2/3. We can change rates of change into decimals, but often for this measurement, it's often helpful to think of it in terms of fractions because it has got those two parts, the change in y over change in x. If I did want to give it as a decimal, then that would be 0.6 repeating. But I'm going to just leave it as a fraction because that's probably how we normally want to think about it. The following represents the relationship between the frame number and the perimeter. Determine rate of change. Frame number, I think this probably came from a different question before that might have had actual diagrams with it. Imagine that let's imagine picture frames that come in different sizes. So frame number 1 was the smallest one, and frame number 2, picture frame number 2, is a bigger one. So let's think of it that way. So imagine a series of 6 different picture frames ranging from the smallest one to the biggest one. So frame number 1, going from frame number 1 to frame number 2, obviously we're going up by 1 frame. And then in each case, if we go from 2 to 3, we're up by 1, and 3 to 4 is up by 1, and so on. So delta x is the change in frame number. Every time I go up by 1 frame, then I increase by 1. My delta y, or first differences, I'm going up by 4 each time. A quick look at that, it's pretty easy to see that it's going up by 4. So the rate of change is 4/1. So as far as units go, because that is a useful thing in this case, to just help us round out our picture, the units would be 4. I'm just going to, if it's 4/1, that's pretty much as reduced as I can make that fraction, but it's 4 centimeters per frame. That would be my units. So what that tells me is that each time I increase my frame, go from one frame size to the next one up, it's going to get 4 centimeters bigger. And the last example, the following represents the relation between Tom's total savings and the number of months he saves money. Determine the rate of change. Okay, no problem, delta x. As you can see, at quick glance, once you know what to look for, it tells us that we're going up by 3 each time. For delta y, or first differences, might need to do a little bit more calculation, but from 345 up to 540 is going up by 195. And 540 to 375 is 195. I'll put the units in at the end, but for now I'll just write the numbers down. Each time it's going up by 195. So rate of change equals delta y over delta x. So 195 divided by 3. If I work that out, then that's 65. But again, I should have units in there. That'll give it some meaning. So that's $65 per 1 month, right? Let me just write that in. Because I didn't show the reducing. Obviously, I hope obviously 195 divided by 3 equals 65. But if I think of it just as a reduced fraction, that would still be 65/1. So that's telling me $65 over 1 month. So the rate of change is $65 a month, and Tom is saving $65 a month. That's the rate of change. If he were to increase his savings to $75 a month, well, then that would be a greater rate of change. Okay, that's it. Take a look at the homework, and I will talk to you next time.